Okay, so the second chapter, computer organization architecture, in that the second unit is data representation and arithmetic. So in the data representation and arithmetic, we'll study about fixed point numbers, floating point numbers, and some the algorithms that related to multiplication and divisions. So if for your examination point of view, you will get around 11 to 12 marks from this chapter. One 7 marks question and one 5 marks question you may get. So around 12 marks from this chapter you will get, and here it is complete. It's a data representation and arithmetic. So here you will study about the mathematical part, mathematical how we represent the data in a computer. Okay, addition, subtraction, then multiplication, division, then floating point data representations, and high performance arithmetic operations. So for this, even means while from next class, you have to keep the pen and paper to solve the problems. Okay, so data representation and arithmetic in computer. Okay, so we'll start with the. So for this, you have to refer in your syllabus. This computer architecture and organization integrated approach, Miles Modoka textbook. So for this textbook, you will get a PPT in the online. PPTs are available. Even I can share through the classroom. So this is the textbook, the PPT I have taken from the textbook, the online, that is computer architecture and organization by Miles Modoka. Okay. So we'll study about the fixed point numbers, floating point numbers, and one of the case study. Okay, so this is not there in your syllabus, character codes. So fixed point numbers. So fixed point numbers means uh, here the digits, the, like for example, so this is the radix point, and fixed point means it's a real number. The real number and the digits are fixed before and after the decimal point or radix point. Fixed point numbers. In the fixed point numbers, these are the real numbers. Fixed point number, these are the real numbers. Real numbers. This is the decimal point. Decimal point. So after the decimal and before the decimal, the digits are fixed. The digits are fixed. So, so this is the fixed point number. There are two major approaches to store the real numbers. That is number with the fractional component in modern computing. So fixed point notations and floating point notations. So we'll study both the fixed point numbers and floating point numbers. So in fixed point notation, there are fixed number of digits. These digits are fixed. For example, 134.199. So the digits are fixed after and before the decimal points, whereas the floating number allows for varying the number of digits after the decimal point. So in floating point, what happens? In the floating point, we can adjust the decimal point. We can shift the decimal point. So in the fixed point number, after the decimal point and before, the digits are fixed. So fixed point data representation. The representation has fixed number of bits for the integer and fractional part. So the left side it's the integer part, it's a fractional part. This is the radix point, and here you will get one more, that is sign bit, sign of a number, either positive or negative. So the fixed number of bits for it has the representation, integer part, fractional part, and a sign. For example, if a given fixed point data representation is like this is the integer part, I indicates integers and fractional part, then you can store the minimum value. The minimum value you can store is, this is the minimum value, 0 0 2 0 0 0 0 1, and maximum value you can store in the integer and fractional is this much. Okay, this is the maximum value you can store. So that is the limitation of fixed point numbers. So the means for large numbers you cannot represent large numbers, you cannot represent in the fixed point representation. We will get some precision errors. There are three types, three parts in the fixed point number representation. That is sign field, integer field, and fractional field. Sign, integer, and fractional field. Unsigned means by default we consider it as a positive. Unsigned a fixed point representation. Signed means we have to consider the sign field bit also. Okay, sign, integer, and fraction. So that is a fixed point data representation. So we can represent these fixed point numbers using the signed representation. Signed representation, the range is from minus 2 raised to k minus 1 to plus 2 raised to k minus 1 for k bits. And we represent fixed points in one's complement representation, two's complement representation. So two's complement representation is preferred in the computer system because of unambiguous property and easier for the arithmetic operations. So we represent the data representation is in the two's complement in the computer. So you already know the ones complement. So what is ones complement? Ones complement is uh, ones complement representation. So 0 is converted to 1, 1 is converted to 0. For 0, the complement is 1. For 1, the complement is 0. So that is one's complement. So for example, so this is the data. So what is the one's complement for this? One's complement of this number is one's complement. What is the one's complement of a number? So 1 is converted to 0. This is the one's complement. 1 ka 0, 0, 1 for 0, 1 for 0, 1 for 1, 0, 0, 0, 1. So this is the, I think you already know about this one's complement of a number. Then the two's complement. So what is the two's complement? Two's complement is that you have to add 1 to the result of one's complement. Yes or no? We need to add 1 to the result of one's complement. This is our original number. This is the one's complement, and we will, after adding 1, we will get the two's complement. 1 1 0 carry 1. So 0 0. So two's complement. After adding 1, here we added 1. So, so this is the 2's complement of the data representation. So the these concepts you know in the logic design, 1's complement and 2's complement of a represent. So assume the number that is 32-bit format. So a 32-bit format which reserves 1 bit for the sign, which reserves the 1 bit for the sign, 1 bit for a sign, 15-bit for the integer part, 15-bit for the integer part, and 16-bit for the fractional part. 16-bit for the fractional part. So 1 bit, 15-bit for the integer part, 16-bit for the fractional. So total how many bits? 32-bit. So we are representing the number in the 32-bit format. 32-bit format. The what is the range? 32-bit. 32-bit. Where 0 is used here. Sign means what? Either 0 for the positive number and 1 for the negative number. 1 for the negative number is used for the sign bit. And here this is the value that in the 15-bit binary value for the decimal. I think it is a 43. How you calculate that? 43, 101011. Here I am taking this one. Hmm? So what to do here? Here the position is 0. So 1 into 2 raised to 0 plus 1 into 2 raised to 1. Here 0 into anything means 0. So don't add. 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. Then 2 raised to 3. Then 2 raised to 4 is 0 because anything into number is 0. 2 raised to 3, 2 raised to 4. 2 raised to 4. So 1 plus 2 plus 8 plus 16. 20, 2 raised to 0, 1, 2, 3, 4, 5. This is 5. Last one is 2 raised to 5 the position. So it's a 32. 32. So 32, 40, 43. So this is the number. The integer part is 43. 43. And so similar to that, this fractional part it is a so this one 16-bit. So the fractional part is 625.0625. So the advantage of using the fixed point representation is the performance, and the disadvantage is that relatively the limited range values that they can represent. So here we are representing the number in a 32-bit format. Suppose if the number is large, the size of the number for scientific calculation and all, the number is very large. So for such a large number, we cannot represent in the fixed point representation. So it is usually inadequate for the numerical analysis as it does not allow the enough numbers and accuracy. Okay, so if the number is very large, then it is difficult to accumulate in a 32-bit format. So a number whose representation that exceeds the 32-bit, if the number that exceeds the 32-bit, then that would have stored inexactly. Means we need to neglect. Suppose for example here for this 16-bit, this fractional, suppose if there is some value like 16, if more than 16 bits, more than 16-bit means we have to neglect the remaining bits. We have to consider only 16 bits. We have to consider only 16 bits. So if it exceeds the 32 bits, that would have stored in exactly. So that is the one of the drawback in the fixed point representation. So here you can see this is the largest and smallest number you can represent. So the largest 15 bit here you can represent, and for fractional this is the minimum value, this is minimum, and maximum this is the range. Maximum all are 1. This is the maximum. Suppose if the number is larger than this, then we have to neglect that. We have to neglect that the bits. So it gives the inaccuracy in the result. Inaccuracy in the result. So that's why that is the drawback of the fixed point numbers. Fixed point numbers. So the fixed point numbers for fixed point numbers for 8-bit number, there are 2 raised to 8 possible bit patterns. 8-bit number, there are 2 raised to 8, 256 possible patterns, and these patterns can represent the negative numbers if we choose to assign a bit pattern to the number. So in fixed point numbers, we represent sign representations in sign magnitude, first complement, two's complement, and excess. These are the different way we represent the fixed point numbers. Signed magnitude, one's complement, two's complement, and excess numbers, excess biased. So this is about the fixed point numbers. Then we already discussed about this one's complement of a number. The leftmost bit, if we is sign, that is 0 and 0 for positive, and so for any number. So like this number, okay, that indicates it's a plus sign. Plus means it is a positive number. Positive number. 1 indicates negative number. Negative number is obtained by subtracting each bit from the 2. So you already know this one's complement and two's complement. This is positive number, negative number. So this is 0 and their one's complement. One's complement. Similar to two's complement, we add one to the number. We add one to the result of one's complement. So positive number, and we keep the sign as 1, and after we'll add the 1 to the, here you can see this is one's complement. One's complement, here 0 is there, and in the two's complement plus 1 is added here. Plus 1 is added two's complement. So you already know the one's complement and the two's complement of a number. So just keep in mind one's complement, sign magnitude, one's complement, and two's complement. So we represent the data for fixed point numbers. Fixed point numbers we can represent in sign and magnitude format, one's complement and two's complement. So that is all about the fixed point numbers. Fixed point numbers. Then we'll go for the floating point numbers. Floating point numbers. Floating point numbers. So just this is one example. You just focus on this example. 6.023 into 10 raised to 23. 10 raised to 23, such a large number. 10 raised to 23. So 10 raised to 23. So such a large number, 10 raised to 23, 6.023 into 10 raised to 23 means there are 23 digits. Such a large number that we can represent means here we are adjusting the decimal point. We are adjusting the decimal point. So that is the advantage of the floating point numbers. Okay. So the number may be, for example, here the 6.023.1.2.4.5 such 7.8.9 up to the 23 digits. up to 23 digits. Such a large number that we represent in this format. 6.023 into 10 raised to 23 decimal number base 10. So such a large number we represent in this format. We are adjusting the floating point. We are adjusting a floating point. So this decimal point. So that's why we call it as floating point numbers. So floating point number, fixed point in that the fixed point. What is the fixed point? The decimal point is fixed before and after the decimal point is fixed before and after the digits. Okay, we can't move at the right side or left side, but in the floating point we can change the decimal point. We can shift. Okay, so floating point numbers that allow very large, very small numbers, very small numbers to be represented using only a few digits, using only the few digits at the expense of the precision. The precision is primarily determined by the number of digits in the fraction, and the range is primarily determined by the number of digits in the exponents. The range is determined by the number of digits here, the exponent 10 raised to 23. Okay, so we represent the numbers in this format: sine, exponent, sine, exponent, and the fraction part. So this is the sine. First field is sine, positive or negative number. Then the exponent digits, then fractional part, then fractional part. Okay, sine, exponent, and significance. So fractional part, significant. Okay. So in this way, we represent the floating point numbers in a computer. In a computer, but in computer there is a one more standard is there, that is IEEE 754 format. We'll discuss that. IEEE 754 format. It's a very even your gate exam also you will get this type of questions. uh, how to represent the number in IEEE format. So IEEE is our computer that stores the data in the IEEE 754 standard. There are single precision format. In IEEE only there are two types: single precision, that is 32-bit format, and double precision IEEE, that is 64-bit. 64 that we'll discuss. Okay, and also we'll solve the problems, how we can convert such a number, how we can convert this number in IEEE format. Okay, so you can understand it is plus, it is a 6.023 into 10 raised to 23. So how to represent this number, how to represent this number in a IEEE standard format, so that we'll discuss. Okay, so floating point numbers, what is the advantage of floating? Such some large number, very large number, or very small numbers. Very large number means 10 raised to 23. Some number into 10 raised to 23. Such a large number we can represent in this small format. Or very small number like 10 raised to minus 54. Suppose 10 raised to suppose 6.02 into 10 raised to minus 56, minus 56. Such a small number, minus 56, such a small number, that also we can represent in this format. So here we are adjusting the decimal point of a given number. So before going to the IEEE standard format, we have to go through some of the basics. Like one of the concept is normalization. So base 10 number, the 254 that can be represented in floating point as you can represent like 254 into 10 raised to 0. So 10 raised to 0 means 1. So you already know. So 254 into 1 means 254. There is no difference. Then 25.4 into 10. There is no difference. So this is also equivalent to 254. 254. Means how we can adjust the decimal point. We can adjust the decimal point. So here 2.54 into 10 raised to 2. So there is no change. So what is the result of this? Here also it is also 254. 2.54 into 100. So what is the value? 254. 0.254 into 10 raised to 3. We are shifting the decimal point to the left. Okay, this is also 254. So this number also 0.0254 into 10 raised to means 10,000. So this is also equivalent to 254. So what is the result? 254, 254, 24. But here the decimal point we are shifting to the left. So for this there is we are shifted the decimal point to the left again. So these are the different way we call it as normalization. We call it as normalization of a number. So that is the beauty of this floating point data representation. Floating point data representation. I hope you are getting the concept. One, two, three. Okay, so there is no the final. What is the result? 254. But there is no change in the. So 2.54 into 10 raised to 2 that is equivalent to 0.0254 into 10 raised to 4. So there is no change. The final result is 254 only. We are shifting the decimal point. So that is floating point representation. Such large numbers we can represent in a small form. Infinitely many other ways which create the problem when making the comparison with so many representations of the same number. So floating now point numbers are usually normalized. So we need to uh, the numbers we need to normalize in which the radix point is located in only one possible position for a given number. The radix point is located in only one possible position for a given number. Usually, usually but not always, the normalized representation places the radix point immediately to the left of the leftmost non-zero digit in the fraction. So normally we represent the is 0.254 into 10 raised to 3, the normalization of the number. Because why it is required normalization means while converting the number to IEEE format and all, we require a number in because means in the exam also they will give the number like 254. 254. So this you have to normalize. You have to normalize this number. What is the normalization means? 0.254 into 10 raised to 3 because it is required to convert the number into IEEE formats and all. So normalized representation places the radix point immediately to the left of the leftmost, okay, non-zero digit in the fraction. Non-zero digit in the fraction. So while in data representation or in floating point representation, we need to convert the number into a normalized form. So here we can see one example. So here this is the number. Huh. So we converted um, because hmm, why it is required means that fraction part 10 dash to minus 2, 10 dash to minus 3 means this is the format for the 754 floating point format, single precision and double precision. Here the exponent bit 8 bit, 11 bit. So for that exponent bit, like suppose if they give to 554, hmm, so for this decimal number, here we can't find the exponent here. So that's why we have to convert this number into the fraction part. So we'll discuss that. So this is one example. Represent 0.254 into 10 raised to 23 in a normalized base 8. It is in the base 10. 10 means what? Base 10 in a normalized base 8 floating point format with a sign bit followed by a 3-bit excess 4 exponent, 3-bit excess 4 exponent followed by 4 4 base 8 digits. Okay, you will understand. I will repeat one more time. So what here they are done is they are converting the target base. What is the initial the original? It's the base 10. Represent this 0.254 into 10 raised to 3 in a normalized base 8. Decimal number is 10. Base 10. Octal means base 8 means octal. Okay. So normalized base 8 floating point format. So this is the step 1. Convert the target base. What is the target base? Octal. So that's why 0.254 into 10 raised to 3. Okay. So this is equivalent to 254. Octal we need to convert into octal format. So for octal format, you have to divide by the 8, 254 by 8. So you will get the remainder 6, 7, 3. Okay, from bottom to up. So you got the 376 as the reminders. Okay, it is in the base 8. So you for you need to shift the decimal point. So 8 raised to 3. So this is your target for represent the 0.254 into 10 raised to 3 in a normalized base 8 floating point format. Okay, normalized base 8 floating point format. So this is the original number. So this is your target. You have to convert into base 8. Okay, then 8 floating point format with a sign bit followed by a 3-bit excess 4 3-bit 3-bit excess 4 exponent. So here it is a positive number. So positive sign bit is 0, and exponent here what they are mentioned followed by 3-bit excess 4 3-bit excess 4 means you need to add 4 to the exponent. What is the exponent value? 3. Okay, 3 plus 4 7 excess 4. Okay, followed by a 3-bit excess 4 means excess 4 exponent. So what is the exponent value here? Exponent value is 3. Exponent value is 3. So we need to add the 4 to that. So what is the result? 7. We'll get the 7. and that is followed by four four base 8 digits. Four base 8 digits. So how many the digits are there? Three. So you need to add one more base 8 digits. कितने three digits है? So you need to add one more zero. You have to make it four. So this is simple example. Means this is the one example with respect to that we have converted. This is the example. Okay. So with respect to that we are converted. So I will explain once again. Means we are converted a number into the binary form with respect to the whatever the conditions they are given. Okay. So the before whatever the concepts we discussed like fixed point numbers, the just keep in mind fixed point number means what? The decimal point is fixed. We cannot shift to the right or left. Decimal point is fixed. And floating point number means in that we have to convert the means such large number or very small number into the floating point numbers. Like we can shift decimal point to right or left side. Okay, we can shift the decimal points. And normalization form means what? Normalization form means some like 254 that we can representation in this form. We have to shift the decimal point at the leftmost bit. Okay. Then this is the example. This is the example they are given. So here what to do? Represent 0.254 into 10 raised to 3. This is the one number they are given in a normalized. Represent this number in a normalized base 8 floating point format. So what is the base here? Base 10. This is the original number. So they are given in a base 10. Okay. And what is the target base? We need to convert it to base 8 floating point format. Base 8 means octal number with a sign bit followed by a 3-bit excess 4 exponent, 3-bit excess 3-bit. So here the this exponent should be 3-bit followed by 4 followed by 4 base 8 digits. Base 8 is the octal, so it should be 4. Okay. So first step is you have to convert the target base. Target base is what? Base 8. Original is that base 10. So convert to the target base. So how to convert to the decimal to the octal? How to convert the decimal to octal? So octal means 8. So what to do? We have to divide by the 8. Like for example, how you convert to binary? We divide by the 2, no? 2 ones are 2 twos are 4, 2 sevens are. So this is the converting number decimal to binary. But what they are asked? They asked about the octal. They asked about the octal. So first you have to convert this into this form 254 and use the remainder method. Find the octal. So for that what to do? 254 by 8. So 31 is the quotient. Remainder is 6. Then 31 by 8. 8 is the 24. Remainder is 7. 3 by 8. Quotient 0. Remainder is 3. So from bottom to up 376. Okay, base 8. So how you represent in the floating point format? 0.376 into base is 8. So 8 raised to 3. Okay. So this is the normalization. We are normalization means we are shifted the decimal point to the left. Okay. So that is your second step. Then in the third step, what? Third step. So you need to uh, followed by 3-bit XS4 component. What is the exponent? Exponent is 3. So you need to add the 4. 3 plus 4. Suppose if it is 4, then plus 4. So here 3 it is. Okay. 3, 8 raised to 3. Then in that you have to add the excess 4. Excess 4 you have to add 3 plus 4, 7. And followed by 4 base 8 digits. So base 8 digits. So how many here? 3 are there. So what to do? You have to make it 4. How you make it 4? 3, 7, 6. You can add 0 here and make it 4. So this is your 0.376 base 4. So now you represent the number in floating point format. This is the sign. Sign is 0. That is positive number. Then that exponent is 3 plus 4, because we are added the excess 4, no? So 3 plus 4, that is 7. So 7 ka binary 111, because and it is octal. Octal means you have to represent in 3 only. Hexadecimal means if it is 4. Okay. So 3760. So the computer, we human beings, we understand in this format 0.254 into 10 to 3. But the computer that understands in this form, the computer understands this binary form. Okay. So this is the how we convert the number into in a binary form. Okay. So in the next class we'll discuss a few more examples